All right, so we've proven that an analytic function on a star domain has an antiderivative. But are there any other kinds of domains other than star domains for which an analytic function will always have an antiderivative? And we respond to that question with a definition. So we'll define the term elementary domain to refer to any domain, any open path-connected non-empty set, for which all analytic functions on that domain have an antiderivative. So what we just got done proving, when we proved the Cauchy integral theorem for star domains, what we just got done proving is that star domains are elementary domains. There might be more elementary domains. So what else is an elementary domain? Well, let's start by looking at something that's definitely not an elementary domain. Just as an example. So take an annulus. Annulus means the region between two circles, or if you like, the thing you get when you take a disk and you subtract a smaller disk. That will definitely be not an elementary domain. So how can we see that? So it's not an elementary domain if there exists at least one function that's analytic on this set, but which does not have an antiderivative. And there does exist one. So I don't know if the point in the center here is actually the origin, but whatever the point in the center is here, I can define a version of 1 over z that is just shifted so that this is like its origin. So if this point is z naught, then maybe the function 1 over z minus z naught. Then if you take a contour integral along a closed curve like that, then you have seen that we get, if I call this alpha, we've seen that you get not 0, but something else, 2 pi I guess. That implies that this function, 1 over z minus z naught, which is definitely analytic on this annulus, definitely cannot have an antiderivative. Therefore, the annulus is not an elementary domain. So finding a single bad analytic function is enough to make a set not an elementary domain. For it to be an elementary domain, all analytic functions have to have antiderivatives. Okay, so maybe that's not too surprising to you, since it's not a star domain, so at least we couldn't argue that it's an elementary domain by our previous result. But non-star domains can sometimes be elementary domains. So, for example, if I take a version of the annulus where I've cut out a portion over here, or if you like, I can just cut out one line and then it would be a slit annulus. If I take something like this, that's definitely not a star domain. If you take any point in here, it will not work as a star center. There will be some other point that's not in visibility. So whatever point you pick in here, there will be some other point, like the point across from it, such that the line segment joining them is not inside. So this is not a star domain, but it is an elementary domain. And one way to argue for that, well, okay, first let's see why, if this is z naught, why does 1 over z minus z naught no longer work as a counterexample? Well, at least I definitely couldn't use that circular path that I used before, because that would not go through, if I used a circular path, it would have to exit the annulus. So my previous methods for method for proving that the annulus was not an elementary domain wouldn't work here. But that doesn't prove that it is an elementary domain. Why is it an elementary domain? So one thing you can prove is that if you have, let's say you have an elementary domain and another elementary domain, and you union them, then is the union an elementary domain? Not always, but if you know that the intersection is a connected set, then yes, then the union is an elementary domain. And the argument is pretty simple. I'll let you read it in the textbook, but basically the idea is if you have, say you have an analytic function on the union, so an analytic function little f defined on the union, then it has an antiderivative on here, because this is an elementary domain, and an antiderivative on here, because this is an elementary domain, so big F1 and big F2. Now on the intersection, big F1 and big F2 both take some values at the various points in the intersection. Since they're antiderivatives for little f, big F1 prime is little f, and big F2 prime is little f. So for the difference F1 minus F2, the derivative is 0. This is where the difference is defined, which is on the intersection. So on the intersection, f1 minus f2 is a function which is defined and whose derivative is 0. Derivative 0, that implies that it's locally constant. But if we're assuming the intersection is connected, then this difference is constant. Connected means locally constant functions are constant. So then, in other words, f1 is f2 plus a constant. So if you just take either f1 or f2 and add or subtract that constant, then you will still have antiderivatives for little f, but you will, by shifting by that constant, you will arrange things so that they take the same values on the intersection. Then you can piecewise define some global antiderivative big F on the whole union, which takes the value big F1 takes on this set, the value big F2 takes on this set, and on the intersection you can take either one, and big F will be a global antiderivative for little f. Okay, so the point is, if you union elementary domains that have connected intersection, then you get an elementary domain. So that lets you prove that a lot of things that are not star domains are still elementary domains. For example, this annulus that has had a byte taken out of it. So, for example, you could view it as I don't know, you could just build it in chunks like this, where each chunk is a star domain, and the overlaps are connected sets. Then the union is a star domain. But you could never fill in that last chunk, and then the union, it's not a star domain, then the union is elementary domain. But you can never fill in that last chunk, because if you tried to, then, like say I tried to fill in this bit here, then the intersection between this and the other stuff would be both this rectangle and this rectangle. They're not really rectangles, but you know what I mean. So the intersection would be these two kind of islands. That would be a disconnected set. So I couldn't apply this idea to try to prove the very wrong fact that the annulus is an elementary domain. All right, so I think the language of elementary domain is particular to our course and the textbook that we're using. So you might not see that language used elsewhere, but it is pretty useful for talking about things with the way we've set them up. In practice, you will see people refer to elementary domains by what they actually turn out to be, which is something we've never explicitly stated. It turns out that the elementary domains are the simply connected sets. So that means roughly subsets of the plane that do not have holes. So this is a subset of the plane that does not have holes, but if I take the annulus without the chunk removed, then there is a hole. So this is simply connected, this one is not simply connected. To actually define simply connected requires some topology machinery that we just have not developed. But if you make that definition, then do some work, then you can prove that a subset of the plane is an elementary domain if and only if it's simply connected. Meaning the simply connected sets are the sets on which analytic functions have antiderivatives. If you want, if you're happy to stick to only working in the complex plane, then you could define simply connected to just mean this. So this would be a way of sort of using complex analysis to detect whether subsets of the plane have holes or not. This set, the annulus, has a hole which we can detect by taking a contour integral of a certain analytic function and around the hole and observing that we don't get zero. And this one has no holes, as we can detect by verifying that all analytic functions have antiderivatives.